All right, good afternoon. We're going to start off our next session, Why Ethernet APL, Unlocking the Full Potential of Industrial Ethernet. Our speaker is Sean Vincent from the FieldComm Group. He is the Director of Technology Programs, and he's also Chair of Ethernet APL Performance.
All right, thank you. Yo, keep going. Okay. What I want to talk about today is Ethernet, APL, SPE are here today. They're available today as specs. They're available in vinyl. You have conformance, you have products. It's still emerging as a technology in the market, but we need to prepare for it. And the reason I say that is when we install things like people, we install infrastructure, we have a long lifespan. So we don't necessarily think about products we need today or even tomorrow, but what are we going to need in 5 years and 10 years? And so we have to start making that preparation today. So we're going to plan, we're going to prepare, and get started today. And the biggest takeaway is that there is an engineering guide of what is necessary and required you configure and plan for infrastructure so that you have a successful installation and successful usage of the technology. Throughout my presentation, you might see this little yellow finger pointing. Generally, try to put in hints and kind of some summary pointers. And so we have the pointing finger to kind of help out. So for the plan, we need to look at where we really get started. And one of the ways we start is by deciding what types of products we need or what types of products are available, because that's going to guide what we do next, which is establish a topology. So either our topology must support the products that we want to use, or we need to identify products that will match the topology we plan to deploy. We've heard multiple people today talk about different topologies, different setups, but what we really need to do is decide how we're going to implement this in an actual installation. And that means we have to look at our cable requirements, we have to look at our product requirements, the areas, the classifications, how the products will be applied. So I also need to consider power. So we have to do a power budget calculation. We have to look at the overall segment or the new power, not just of the individual products, but of the overall unit or functional entity that we are going to be certified. We also need to consider the performance. We need to look at what are our true expectations for communication and for bandwidth availability, because we can't fill it up to 100% with just regular communications. We need to also allow some overhead for those asynchronous events that occur periodically. So need to know our local requirements. If we look around the world, there are different requirements for what is a hazard, how we handle a hazardous area. So in some areas of the world, we use HATEX in the EU especially. We also use the IEC-EX. That's generally globally accepted. And here in the US, we often use the FM or UL models, the RTL, and we hear a lot of non-intended where probably not so much intrinsic safety in the US. We do a lot of explosion tools and things like that. And so intrinsic safety certified products can be used in non-intrinsic safety applications. Of course, once you use one of those applications, you can't reapply it to intrinsic safety applications, but we can use Ethernet APL and single pair Ethernet products together. We can use Ethernet APL products in areas that are non-hazardous. We can use Ethernet APL products on non-intrinsically safe loops in seconds. That is something that we can plan for even today. So 2Ys, the 2-wire intrinsically safe Ethernet, is the ATEX and other approvals for our Ethernet APL products. But those products, even with those approvals, can be used in non-intrinsically safe applications. We have different types of approvals, of course, within intrinsic safety. And for Ethernet APL, the products are targeted to the highest gas, the highest dust. In other words, the most restrictive, and therefore the product can be deployed in any application. We know that when we get an Ethernet APL product that has a certification, entity certification, we know that we can apply that product safely. That is a big change from how we traditionally look at products in more traditional applications and defense. We also need to consider our code compliance, local regulations, being either regional or our national regulations. We need to look at what it really means. We know we have zone 0, 1, 2, or we can have division 1 or 2, we can have unclassified. We have different terms. We just need to know what is our local regulation, what is required for installations where we are planning to deploy, because we may be engineering here and deploying elsewhere, or it may be engineered elsewhere to be deployed here. So we need to know really where's the target for the installation. So the circuit classes, the types of power that's going to be available within the products are also going to be determined by where we're using the different products, and also determines what's actually available and legal to use in different applications. So we need to determine the types of cable. We have to determine the work practices. We have to consider things like, for example, is this going to be an electrician's job or is this going to be an instrument tech's job? We get different rules of operation in different regions based on the power available on the wire. We may not be able to use the same route to do the full installation. You may have to have a mixed trade for installation. You may have a variety of trades to accomplish the final installation. So it's really going to vary by location. It's really going to vary by the local law. The other thing we need to think about is, as we start to plan, we need to think about placements. We need to think about how we're actually going to install the cable and the pumps. We don't want to put things into a high-risk area. We don't want to have things that are going to get run over. We don't want to bend cable beyond the bend radius that's described by the manufacturer. We don't want to kink. We don't want to have excess cable, but we also don't want to have too short cable. We also need to think about protections beyond. We need to think about things like lightning arresters. We need to think about those are driven by also some of the local requirements. And those also have an impact on our overall planning of the network. Any component in the network is going to impact the power. It's going to impact where we can apply that circuit while we're deploying those products. So we think about, is it going to be marshalling cabinets? We're going to have field cabinets? Are we going to be powering directly? Or we can power through the trunk? All those have an impact on the routing. All those have an impact on the types of cable, the way we protect the cable, and the way that we install the cable. One of the other key things to think about is temperature. Right? Different products have different temperature ratings. So within Ethernet APL, we test products to their min and max temperature ratings as are declared by that product. But different products, different markets have different ratings. So you have to ensure that for your facility or for your application, your location, that you're identifying products that have the temperature ratings that you need for the type of installation that you're planning to. So the connection choices are fairly standardized. You really get a choice between screen clamps, screw-in terminals, or between other types of screw connectors. Traditionally, in process automation, with the 3-terminal situation, we see plus minus shield. One of the key things that's a little different from what we've traditionally done with other, call it 2-wire installations in the past, is that they mount the plus and the minus next to each other, and then the shield between. So now we have plus minus shield in a row. So that way the shield is between each grouping of communication cables. In the past, a lot of times we would do plus shield minus, and we'd have the shield between the plus and minus conductor. We moved it because it gives us a little extra spacing in our circuits. We have a line of connectors. We don't have any interference, but it's something we have to think about when we're installing. We also need to be very careful with the shielding, because now we're going to install the shield in both ends. We're going to have some of the other installations that didn't pass, but we drain the shield all in one end, we drain the cabinets. That's no longer the case. Now we're going to drain the shield both ends, connected. So we also need to make sure we're looking at our grounds. We're going to need to do research on those in advance and determine that we have a good ground that meets the requirements for Ethernet APL before we get started. And if not, you need to take the actions that are recommended to bring the ground up to the requirements that we have for implementing or for deploying APL. So we need to plan accordingly. APL cables, there's a lot of cables in the market. Most of those cables are probably great. A few of those cables may not meet the requirements. And so one of the key things is we need to look at the specifics of the cable that we're planning to use, or we need to find cable that meets the characteristics that we need. The different cables have different characteristics. Even when we talk about field bus type A cable being the cable for Ethernet APL, even within that type A cable, over the years, the cable has kind of changed in where it falls within the range of type A cable. So now for APL, we're on a very stringent requirements around the cable. So we still will need to check, even if we have type A cable, you still need the testing, because over time, the way it's handled, it's also even the manufacturing process that was originally used, it may not meet the requirements that we think it does. So testing the cable is a key component to this. We also need to look at, if we're going to have intrinsic safe and non-intrinsic safe cable, there are different requirements and rules depending on your global area as to how those cables are grouped, colored, labeled, and how they're managed. We really need to take that into account as we're doing our planning as well. So if we really sum it, then the typical purview SPA or field bus foundation, field bus H1 cable, those cables are really the target for what APL was designed for. And that's really what we're at, but we still need to check. So the maximum cable length, you often hear people talk about 1,000 meters, because that's the long reach, right? That's the longest trunk. That's the longest distance. But the longest spurs are 200 meters. So when we talk about cable lengths, you have to think about, where are we talking about it? Is it the trunk, or is it the spur, or is it the combination of the two? We also need to look at the different types of cable, because different cable with different characteristics, it's going to have a different length. So the requirements on the cable characteristic will dictate how much that cable we can actually deploy into the facility. A lot of factors that we have to take into account in the planning, which is why we have an engineering guide that walks us through the process and helps us with those selections and helps us with those decisions. So the topology, we have to think about, are we going to use field switches where they're powered in the field? Are we going to have a power switch that's powered by the trunk and then powering the switches in a multi-drop scenario? Are we going to have individual switches powered? Or are you going to deploy devices and sort of fully loading switches? Or we want to balance our load on the various switches? We have a lot of questions that we want to ask ourselves as we're planning and we're preparing for this. But the general rule is that we're going to have a trunk, or we're going to have multiple spurs. For every trunk, we can have multiple spurs, but for every spur, we have a single device. Each spur is one device, and each trunk is multiple devices. When we think about that, we also need to think about risk factors. How risk tolerant are we of a trunk loss, but all the devices on that trunk perhaps getting lost? We need to think about how we map these out and what devices we combine together before we go into that. Network loading. It's a very important topic that's not related to a specific protocol or to specific users, because within Ethernet APL, we are a multi-protocol support. It's a physical layer. So we can have cameras, we can have IT infrastructure, we can also have field devices all sharing the same data highway using different protocols and different communications. But with all the traffic, we have to consider the shared bandwidth, because while it's a shared physical layer, the amount of data that we can pass is still going to be topped out for the entire network. We have maximum, so we don't want to exceed that. So one of the things we need to consider is reserving some bandwidth for future expansion. We also need to reserve some bandwidth for the life cycle system, for adding in things like additional instrumentation. But we also may need to look at, are we overloading the traffic? They don't want to go 100% bandwidth, because then we have no overhead for any kind of acyclic communications. So we want to make sure that we have the network floating under probably about 80%, right? You want to be somewhere between 20 to 50% of your bandwidth, typically for the cyclic communications. Probably going to have your different protocols. We have some acyclic configurations and some monitoring that's going to happen. So you really will do that loss. And what you see here is an example of a study of devices, the amount of bandwidth, and you can see it quickly gets out of hand as we add a lot of devices into the network. So we really need to think about that. As I mentioned, risk management, the loading of the communications, both the power and the communications. We also need to think about the loss of those products. If we have not only 50 devices on a single trunk, maybe that's not a problem, but maybe that exceeds your risk tolerance. So just because you can doesn't mean you should. We have to think about what really is logical in our network topologies. And again, our risk factors may vary even based on where it is in the system and what products are being deployed. So let's take a look at a example network. So in this case, we have the switches that are separately powered. We also have the devices that are each connected to a single port. Right? Each device has a single port. So we have a single spur for each device. We then have different devices located in different areas. So we have the switches that are outside of our in our elevated area, and then we have our low stringent in our devices. So in this case, we have link limitations that mean we may need to place the products in a way that accommodates the cable that we can support. We have to look at the power drop. We have to look at the power draw of the individual products. And we need to plan for what we want as far as the trunk loading and also for any future products we add in, and think about network restarts and think about all the devices and switches can be accommodated in the areas where we need them. We may need some special enclosures. We may need to plan out our 24 volt or other DC power to supply these. We have to really plan that out before we start deploying these products and finding that we're kind of missing or short rules. So we need to have training for usage, right? We need to train our people before we hand it to them, right? That means training both the people who are going to install it, people who are going to maintain it, but also training those that design it and build it in advance. You need to know the proper installation requirements and techniques. We also need to ensure that all the products are fulfilling the requirements. And we especially have all dealt with suppliers who make a substitution, say it's just as good as the other. We have to watch that. We have to make sure that whatever products we substitute are up to the expectations we have for the engineered network, because Ethernet APL is an engineered network. It's not a plug it in and hope it works. It's design it first and then ensure that it works in the design before you deploy it to the field. That's a key step that we must take. We want to start small. We want to think of the future, but really we need to inspect what we have. We need to think about what we really need. We then need to measure, make sure that anything that's already installed, existing cable, existing infrastructure, that it's up to the task at hand, that it can support products that we want to install. And then once it's installed and designed, we want to make sure that we can confirm and we verify that the products are operating and they're designed and as they were engineered, but also that all the cabling is installed correctly and confirm that it is the correct cable in the correct locations. So when we're looking at cabling, we do have possibility of cable reuse. There's a lot of really good quality cable that's been installed in the last 25 plus years. And some of that cable may still be good, may still be usable, but we don't know until we check. So there are guidelines for how we test the cable. There are guidelines of what we're looking for in the cable, but there are also tools that have been built that will help us with that budgeting, right? There are tools that can help us to test the cable. And just because we tested a single cable doesn't mean they're all good, because if they're kinked or if they've been bent or the radius exceeds what the manufacturer recommends and they're under stress, it may not be a problem for what we're using today. But as we move to APL and as we move to the high availability, those issues become much more prevalent and much more noticeable. So measurements include things like lengths, but also the identify any shorted wires, any broken wires. We need to look for things like a cable break, like we heard earlier. But most importantly, we're looking at basically the signal noise ratio, assertion loss. We're looking at how what's the quality of the signal that we're going to have. So when we're looking for an installation, one of the things we can consider is that if we have the desire to create an overall network, then if we're starting with a large project, we want to engineer that out, decide what products we need, where to place them, and then look at what infrastructure is already in place, and we see is it up to its task. If it is, great, it can move forward. If not, then we need to that we probably need to supplement it. Maybe we need to make some upgrades to some areas. Could be that, hey, the cable we have is great for spurs, but maybe we need a new trunk. Or it could be that the cable we have is good for everything we want to do. But previously installed cables do great. Just because it met requirements 20 years ago does not mean it still meets requirements today. And that's why we need to test and measure. And also, we need to think about that cable will degrade over time. If we install it today and we don't use it for 20 years, it also may not meet requirements in 20 years. So we have to look at different upgrade points. We have to confirm that the cable is still, and all our installation products are still up to task at each of those steps. And one of the biggest things we can do is buy registered products, certified registered products, right? Secure conformance for Ethernet APL. And one of our big things is to make sure that there is conformance and that products are tested and that things are up to test, right? So that's always important, is to know that what we're installing actually meets the requirements at the start and has been verified. It's not just trust me, it's on the label, and sometimes it gets sold something. For power and grounding, we do probably need to put in some kind of surge protection. If we do put in surge protections, then we need to look at, which are often required based on the areas where they're installed, tank farms, etc. But we do need to consider that this is a product in the network. So surge protection devices are what we call an auxiliary device, and there are limits on the number of those you can have in line and cable. We are going to put something in the cable. It's going to count towards the overall engineering. We don't engineer based on just a straight cable. We have to think about the actual breaks in the cable, where each of our connections are, the different switches, the different lightning arresters, surge protections, all these types of products. We have to make sure that those are considered in the overall. We also have to look at the ground. So in functional bonding and shielding, we want to avoid potential differences between our grounds. We have to go through our full checks to make sure everything is up to spec before we proceed with the installation. And if not, we have to follow the mitigation techniques to bring those grounds up to spec so that they meet our requirements, so we have success in our deployment. So we need to create the drawings. We need to show all the power, the cable grounding, all the signal grounding. We need their differentiation of each of those. We also need to make sure that cable shield is grounded on both ends, and that we have to make sure that everything in ground is of a spec. And then we also need to make sure any materials that are necessary, we have good meshing, right? So that we have any tiebacks in our grounding installation. So graphic on connection of temporary products. We talked about 4 inline connections. In this case, if we're going to have an inline connection, could be surge protection or some kind of a resistor product. So in this case, we would have each of those breaks would be an inline connection. And as you see there, we do have a limit of 4 inline connections. And then once we get into the switch, in this case, now we're going to have one connection that goes to each device. And in one of those spurs, you can see we have an additional inline connection, and that is the first cut. So we do need to make sure that we are not having an overall too many connections, too many products, too many breaks in the wire. And that also helps us to ensure that we're meeting all of our needs for noise and also for the overall needs. So this is something that we can migrate to over time. And today we have a lot of 4 to 20 milliamp type products in process automation. All the way over on the far left here, you see that there's your typical 4 to 20 milliamp installations going into IO, going into remote IO. But we can also bring in APL switches, and we can bring in gateways, and we can then bring those 4 to 20 milliamp art products and things that are in those older analog networks into APL. And we can do that over time. There's also several guides, technical papers that have been published about how we can create APL switches that also can lock to more of the intelligent networks to bring those in. And so over time, we can migrate from whatever we're using today to APL. So that's one of the key things, is we don't have to be all in on it day one. You can make a migration over time, but again, we have to plan the infrastructure, plan the networks, and think about where we're using the different types of products and what each of those products need. So the overall experience that we've seen thus far and those that have ventured down this path is that we need to reduce cable usage, right? So we're now going to be using a higher quality cable than what we used in 420 milliamp. So it doesn't necessarily mean that we're going to have the same cable, but we're going to use less cable overall to install one of these networks. And we also can use our control room area, which is critical in some applications, some platforms, and some remote areas. We also can reduce the device commissioning time. And that's because we're engineering this network in advance, right? So we know that when we plug things in, that they have the power they need. We know the products work before we install them. So when we deploy them, we expect them to move in function. We also can increase the number of inputs because before we're thinking about a 420 milliamp type application with the 2 wires, you had a single measurement point made over that 420 milliamp, and now you have an Ethernet network. So we have a much larger number of measurements that you can bring into a system. And also the recovery time is a lot faster. We can detect faults much sooner. We can recover from them much quicker because of the speeds in the network, also because of the engineering of the networks, and we'll know what to expect. We can look for the characteristics, and when those characteristics change, we know we need to take action. So again, we'll get started today. We'll do this by planning. You need to install good cable. You need to test it. We need to make sure that what we have is going to meet our needs for identify what will actually fulfill what's missing in our facility. We then need to think about our future needs and where we want to go with the products. And then you need to be ready when the products that we need or want are available. And we only do that by starting today. We can't wait and start a project that we want to have operational in a few years. You need to start that process now with the engineer. And to get started in engineering, you can visit multiple sites, but we all offer the same document, which is the Ethernet APL engineering guide. And that Ethernet APL engineering guide is available from the organizations listed here. These links actually go to it on each of the organizations. And we're happy. We also have a QR code around the corner that you can scan and get a direct copy of the guide in PDF. But it's a good place to start. And I would say that all the information in this presentation is contained in the engineering guide. So it's definitely something that you want to read before you get started on a project.
Does anybody have any questions?
I think that's the message from the design television. No receivers on the side now. It says the machines, but it overall that was the and redundancy and liability. What I was doing, Steve, or testing to doing in the biggest deliberation different in terms of goals is the normally re those is required testing will are done for 50 or meters.
Well, it's going to depend on what is the target. So some of the protocols today require TSN's protocols, right? So the protocols have high availability and have those requirements built in. Others don't have those requirements because we're designed in different ways. So it comes down to the need for the network, the need for the process. And from the process automation background, I deal a lot with chemical plants, oil refineries, and things like this. And we make a lot of steam. And all we're doing with steam is we boil water. And whether you're measuring the steam in the water at 10 milliseconds, 8 seconds, it's boiling water. Thermodynamics of the water boiling doesn't really change, right? The watch pot never boils is what my mother always said, but I can say that's false because I have watched the pot boil. But when we're making these systems more efficient, it helps to have, there's a crossover point depending on the application where the higher availability and the higher speeds help us. But then there's a crossover point for beyond that, you really don't get any return. And we're just wasting the bandwidth and wasting the effort and the money on the higher of it. So we have to look at the process and determine what we're doing. If we have a tracker, sure. And look at, then we probably need a little bit higher speeds. But if we're making steam, we don't. Process in process oriented for me. So
Do you have